Welcome to today's webinar. The topic today is geotechnical analysis in Rfem 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Alexander, but my two colleagues can introduce themselves.
Hello, welcome also from my side. My name is Juliane Stopper, ACTA. I'm working in the Dlubal team for customer support, and I'm also working for the developer team's concrete design and geotechnical analysis. And I will present this webinar to you, but before I will give the word to you, Alexander.
Hello, also from my side. My name is Alexander Mayhofer. I'm the head of product engineering concrete. So I lead the development of reinforced concrete design and also work in the development of the geotechnical analysis add-on. Today I will answer your questions in the chat.
Okay, thank you for your introduction. Then we can switch off the webcams so the attendees can see the full screen. I say some words for the attendees who participate the first time, how you can ask questions. You can show the control panel on the right side of your screen with that arrow, and then you can enter your question here. And Alexander and me will answer you. If you don't get an answer during the webinar because there are too many, you will get an email in the next days. Yeah, and the other way is to watch the entire webinar and then email your questions to info@dlubal.com. Before I hand over the screen to Juliane, I would like to invite you to the Digital Bau in Cologne. Yeah, you can secure your free ticket if you book a live demo of our programs. Yeah, just click on that link here, or you can scan the QR code. Then you get your appointment and your free ticket. Yeah, okay, then I hand over the screen to Juliane. Just a moment. Okay, Juliane, it's your turn.
Okay, thank you. Thank you, Andreas. Before we go to the program, I will show you some short slides. We start with the agenda that you can see already. I will read it to you. In the first step, we will have a look at some theoretical background, some basics regarding the geotechnical analysis, and we will work about the definition of the soil materials. In the second step, we will create boreholes in Rfem 6, on the one hand in the classical way, and on the second way by using web service. After that, when we have boreholes in our model, we will generate the soil massif, the soil structure that shall be analyzed. We will have a look at the concrete building also and the loads. After that, we will have a look at the analysis. We will check the settlements and the soil pressures for the reinforced concrete building. And after that, we finished the main part. We will have a look at the printout report, how we can document all this model and analysis. And after that, we will have a short summary and we'll also present some prospects, some topics that are in development currently in our team. Okay, that's enough for the agenda. We will start with the short slides regarding the theoretical background. First topic is the material models. Soil is a three-phase system consisting of soil particles, water, and air, and it has a highly nonlinear behavior. For being able to model soil well enough, it is important that you have material models that are able to represent the most important soil behaviors, let's say. Therefore, we have in Rfem two models. We have the modified Moore-Coulomb model and the nonlinear elastic model. We have three further models under development, but this will be told in the prospect more in detail. Yeah, so let's have a look at these current models. The modified Mohr-Coulomb model is a linearly elastic, ideally plastic model. It shows linear elastic behavior according to Hooke's law in a range of allowable stresses, let's say. And when the yield criteria according Mohr-Coulomb is reached, it shows ideally plastic behavior. The Mohr-Coulomb model is a relatively simple model that can be used for deformation calculation without reversion of load. Then we have the nonlinear elastic model in our program. It's a model that is able to show the stress dependency of stiffness that soil shows. So this means that dependent on the stiffness state the element is under, it shows a different stiffness. As the different stress state, it shows a different stiffness. And it is also able to differ between first loading, primary loading, and unloading and reloading. In unloading and reloading situation, it shows linear elastic behavior. This model is suitable for deformation calculation, including lower reversions of load and with distance to the failure. Okay, so far to the models. Let's come to the next topic. This slide shall show that it's important that the supports, our soil needs to be supports, it's supported by surface supports, that these supports have enough distance to the area you are interested in, so that this support stiffness doesn't influence your result, or don't influence your result. And you can find proposals in the literature regarding these distances. Here I'm showing an example from the German Geotechnical Society. You can use such recommendations as orientation, and after you calculated your model, you can check the boundary surfaces, and you can check how the stress changed and whether your boundary surfaces are far enough or can come closer to the range, to the area you're interested in, or the part you're interested in. Okay, then we can come to the third and last short theoretical slide, the geostatic stress state, or the initial state. As I said, we have this stress dependency of stiffness in soil behavior. So if you want to analyze your building with the right stiffness, it is needed that you know the stress state your soil is in. So what we do is, in a very first step, we calculate the geostatic stress state. We analyze a load case for self-weight of soil. In this load case, the self-weight is applied and the stress state for all the elements of soil is calculated. Then you have in each element the right stress state, and then the right stiffness can be used for the further analysis for your building. If you would start without this initial state, without this geostatic stress state as primary loading, all the elements would start from 0 in the material behavior, and all the elements would show stiffness, this stiffness that I show here. And this would not be right. All the elements dependent on their stress state show different stiffness. So what we need is we need the stress state. We get the correct stiffness. What we don't need is this displacement that is calculated as well. We are not interested in the deformation that happened to the soil due to its self-weight. For us, if we look at this picture, this is the start situation, and we want to know the deformation that happens for the further loading. So what we do is we reset this displacement to 0. So we have the stress state, we have the correct stiffness, and the deformation is set to 0 so that it starts to count the deformation from our further loading from our building. Okay, but we will see this in the program as well. That's enough for theoretical backgrounds. We now go to the program. I open Rfem 6, and what we see is our concrete building. It is prepared so that we can today focus on geotechnical analysis settings. The first step that we do is we go to the materials. I open it, the dialog for materials, and we see the materials we have in the building. I did prepare the input, and we will now go through it. When we have the geotechnical analysis add-on activated, we have the material type soil provided. So we have basic, we have soil, and if you select soil here, the specific soil material models are provided as well. Today, I want to use the nonlinear elastic material model in our webinar. Our soil materials, they are always user-defined materials. So it's activated and it's not editable. This is done because you will have always project-specific values for your soil. You will always have to modify the values and enter values. We, of course, provide some materials in the library, but we will see this later. Here on the right side, you can enter some basic material properties. And for soil, we have the specific weight which differs between drained and saturated, so that it can be applied dependent on whether the soil is under groundwater level or above. Yeah, and when you have a specific soil material model selected, this specific register opens, and here you can enter the further material parameters this model needs. For the nonlinear elastic model, we have at first here the option to enter the shear strength parameters like cohesive strength and angle of internal friction. And on the right side, we can see a drawing that a scheme for the material model behavior. And here you can see the equation that is used. So we enter the shear strength parameters, and what is needed else is we need a reference stiffness that is we get from soil tests, from laboratory tests, and this stiffness is tested with for a reference stress. So we need these two. We need for a stress the tested oedometric stiffness. We have the shear strength parameters, and then for each stress situation, the related stiffness can be calculated by the model. We also have here this M value. It lies between 0.5 and 1, 0.5 for sand and 1 for clay. This influences the stiffness, the stress dependency of the stiffness. Yeah. If you are in our dialog here for the specific soil material model and some questions come up, you easily can use the set button here. I want to shortly show it. It brings you to our online manual, and you can check some background information and see some hints and so on. But this is a short tip. Let's go back to our dialog. Okay, in our model today we have a first layer, a kind of filling, then we have a second layer of sand, then we have a till, and then a second sand with higher modulus of elasticity. What I want to show is also shortly the library. We have the library here, and if you select material type soil, as I said, we also propose, we offer some values that you can take over if you want to just model an example or something. You get values here too. Okay, but I will cancel this and keep my prepared values. That's it for the material. In the basic objects, we see that there are some other objects that already exist. They belong to our concrete building. We will go on with the input for geotechnical analysis, and therefore we go to special objects. In special objects, you find here the option to enter the boreholes and the soil massifs. We will start with boreholes. I will open the dialog. Boreholes allow us to directly bring the values from the geotechnical report to Rfem. We can enter for a specific location along the depth, the material, and the material parameters. And this is what we will do now as a short example. I keep 0 as location for this example. Here you can enter the groundwater level that was discovered by the field tests. And here you can enter the layers that were discovered. And you start from 0 into the depth of the top of the soil. So we start with our filling, and we have sand. Then we have this, and we have our second sand layer. And of course, you need to define the thickness of the layers. This is just as an example. We have 2 meters of this and maybe 20 of this. Here you can see a scheme for your profile. You can see the different materials, and you also have the option to print this, to print out report or to clipboard, to file, and so on. Okay, that's it. That's enough for our borehole. We can now see it in the model. It was placed to the location that I entered, and it is here now. And now I could go on and define more and more. You can find the boreholes also in our table. If you are here in structure and special objects, you can find here this register for boreholes, and you can find the list of boreholes here with the coordinates. And you have this small icon that shows that groundwater exists. And if you double click here somewhere, the dialog opens again. Yeah, that's the classical way of entering our boreholes in Rfem 6. I today want to show another way that we provide. We want to use web service. You have the chance via web service to communicate with Rfem 6 via different programming languages. And in this case, in our case, it was done with a small C# program. This program was prepared to read borehole data from a list and write it to Rfem 6. And the file that I will present, the small program, we will provide to you with the webinar documents, with the webinar files. Okay, but now I want to show the table that we will read. This table is a list of our boreholes with the coordinates, and we here have the information about how many layers the current borehole has, and next to it, it needs to be filled the number of the material and the thickness of the layer. And you have to take care about that the number of the material fits to your input in the Rfem 6 file. So I did take care of that, and I have my list prepared, and now we will start our short application. Before we start it, maybe a hint. If you want to use web service, you should check here in options, program options, that you have the web service active. You have here this checkbox. It needs to be active so that web service can communicate with Rfem 6. Okay, now we will run our application. I will go to my file where I have my Excel file. Here it is. I will now start it, and we will see what's happening. At first, it reads the data. Yeah, now it did it. Now it will connect to Rfem. Rfem will be logged, and it will write all the data, and then again allows me to contact Rfem. Now it's writing it, and it is done. I have all the boreholes of my list in my program now, and it can be imagined that it could be much more boreholes. It would be quite comfortable to write them into Rfem like this. Okay, so that's enough for the boreholes. As you can see, if you have some processes that you do again and again for your kind of models, it can be useful to use the web service and make the work easier. Okay, we have now the boreholes and we can create our soil solid from that, and therefore we open the soil massif dialog. In that soil massif, we have the option to directly generate a soil solid from our data from the geotechnical report from the boreholes. Therefore, I have to assign the boreholes that shall be used. I know that they have numbers 1 and 5. You could also check it, select them graphically. Now I want to graphically set the center of my soil massif. It shall be central below the slab. It was filled here. Now I have to define the size. The top surface is calculated from the top coordinates of the boreholes. Then we give the size, the width in X direction is called A, is 60 meters, and then Y direction B is 50 meters. The depth of the massif is also, as default setting, taken from the boreholes, but it is possible to edit it. You can uncheck this box, and if you want to make it smaller, you can make it smaller. Okay, and we can activate groundwater if we want to consider groundwater for our soil solid. That's it. That's what needs to be done for our soil massifs. We will say OK and have a look at our soil. Now we see that our soil was generated, and we check what is contained. We now can find in basic objects that some solids were generated. We have for each layer of soil, we have an own soil solid. The layer surfaces, they are approximated dependent on the depths that we gave by the boreholes. Then we have the groundwater surface that you can find here. That was generated, also dependent on the groundwater level that is given by the boreholes. And we have surface supports that we can find here in types for surfaces, supports. Here we can find our supports. And we have one type of support for the vertical boundary surfaces. These are supported sliding, which means in the direction vertical on these surfaces, the deformation is not allowed. And here at the bottom, we have a fully fixed support. Yeah, you can see here. Yeah, that's what the creation of the soil massif does. We can see that the solids, the supports, and also our groundwater surface was shown in a different color here. This shows us that it's a generated object. Here we can see it's generated, and we can also see here in the bottom, it's generated and it is connected to the parent, to our soil massif. This means that if you do changes in the soil massif or in the boreholes that are contained in that soil massif, automatically our your soil solids will be updated, and if needed, the groundwater surface and the supports. This is the one option. You also can change this situation. You can change here the massif type, the soil massif type. In the dialog for the soil massif, you can switch it to set of solids. Then this generated state is cut, it's disconnected. This makes that there's no dependency anymore. So your solids wouldn't be updated if you would change something. It in the same time allows you to edit these objects freely. Yeah, that's just as a hint regarding the soil massif. Okay, But that's enough for us. We have our soil created, we have our building created. What I want to do too with you is I want to create a surface contact so that no tension will be allowed between the slab and the soil. Therefore, we are at the right place in the special objects. We have the surface contacts here. I double click on it and we select the surface of our first group. It's the top surface of our soil. And here I select my slab. I take the small area there and this one. And my new surface contact is prepared. I have a surface contact type here, failure under tension, assigned. I say OK, and I create a new one, again on the top surface of my solid. And now I want to assign these columns footings here. I select these surfaces. Now they also wouldn't allow tension. Okay, now I have my building, I have my soil, and I have the connection between them defined. Maybe one hint also, if you want to create a surface contact, there needs to be a distance between these two surfaces. Okay, now we have our model prepared. What we need now is the mesh for the analysis. For the mesh, we can go here to the Calculate menu, and there we find the mesh settings. I click on it, and what we see first is the general settings, and here you can see the target length. It gives the length of the finite elements that shall be used in our model. And when we look at our model, we see that we have quite smaller dimensions in our building than in the solid. So our solid actually needs a different mesh size. And therefore, we did create here in the solids register an own option for you where you can write the wished size for the soil solids elements, finite elements. And we have here the 2 meters and the general is 1/2 meter. So this is fine for me. I say OK and apply, and our mesh generation will start. Our mesh will be generated for the building, for the solid. And we can have a look at this. It's nearly done. It normally is not that slow. It is related to our GoToWebinar. It would be done normally already, but yeah, now we have it. Here we can see now that we have a more coarse mesh in the soil solid and a more fine mesh in our building. That's what we wanted. It looks good. If you want to know, you can go to Calculate, and you also have here mesh statistics. Here you can see how many elements were created. This is quite useful. Okay, now we also finished our topology. We can now care about the loads. I would like to show you which loads we have. They are already prepared. We have self-weight of superstructure. This is calculated from the objects and its material. We have a dead load, we have a live load, and a snow load. With this button you can check it, uncheck it. Now we want to go to the dialog, because as we remember regarding our slides, we need one more load case. We need our initial state load case. We want to, before we can calculate the building, we need to know the stress state of the solid, and therefore we need a load case, self-weight of soil. So I prepare my load case, self-weight of soil. And this load case has an own action category. We can find here at the bottom, it's permanent soil, it is called. And when you activate this, the description for this checkbox here changed. We now have the self-weight active for soil solids and for soil solids only. So this is the perfect load case for calculation of our stress state of the soil solid. And if we look now here to the self-weight of structure, we can see that the description here is that self-weight is active for everything except of soil solids. So with that one, the self-weight of the superstructure can be calculated. Okay, so we have this prepared. Then let's have a look into the static analysis settings. Here you have settings regarding the analysis, and I did already enter load increments 4. Here you can edit it if it is needed. As we have a non-linear material, we have to give it in increments. Okay, I will now create a copy of that static analysis settings, so it contains nearly the same. The only change I'm doing now is I activate this option, the equilibrium for undeformed structure. This is the option that helps us for our initial state, for our geostatic stress state for the soil. With this setting, our structure is solved, it is loaded, and the stress state is calculated, and the deformations that are calculated that are reset to 0. That's why we write for undeformed structure. So this is perfect for our initial state. I will rename it so I can understand later more easy. What is this? It's actually SA1, but for undeformed structure. Call it like this, then we know it's nearly the same setting. Okay, so I assign it now to our load case for soil self-weight, and then we have it. Okay, that's enough for our load cases. I can go on apply, and I will go to our base register because I want to use the combination wizard. I want my load combinations to be generated. Then we can go to actions. Here we can see our action categories that exist in our model. We can see design situations, and I want to not have the ultimate limit state and the characteristic active. I only want to use quasi-permanent today with you. What we can find in our design situations dialog also is here the combination wizard. If you want for the current design situation the load combinations or result combinations to be generated, then you need to assign a combination wizard here, and we can check the settings if we click on here. I have the static analysis settings, the normal static analysis settings to give for my load combinations. We don't have imperfection cases, we can switch this off. What we do have is the initial state. We want and we need that an initial state is used for our load combinations, so I activate it here. And with the activation, you maybe saw it, this specific register opened up. And here you can say what shall be used as initial state. And we select now our self-weight load case for soil. It comes now over here, and here you have also the option to change the type of initial state, but final state is the right choice for us. So everything is taken over. Okay, that's enough. So keep in mind, if you want to use the generation and you want to use an initial state, you can find it in the combination wizard. Okay, we agree, and we can see how the action combinations are generated and the load combinations as well. Okay, and if we have a look on here, we can see that it worked. We have our initial state assigned, and the self-weight for soil load case is used. And yeah, maybe a hint, this second color here gives the color of your analysis settings, and this can be quite helpful to very fast see whether there's a fault happened or not. I can now easily see that my specific for undeformed structure static analysis settings is used for this load case, and here I use the classic, so it's as planned and it's okay. Now I can agree and I have all my loads and load combinations prepared. Good. That's fine so far. Now we are at the point that we could start the analysis, but before I do this, I would like to go with you to the printout report and create a new one so that later we can directly print graphics in there. Okay, I double-clicked on it and opened a new one. I want to check all to uncheck them all. I want to create a simplified printout report that focuses on our geotechnic settings. I use base data and mesh settings, and of course our material. And if we have these specific material models, you should open this menu, and here you can find our soil materials. And we did use the soil nonlinear elastic model. So if you activate it, you will also have your specific material parameters that we entered in the second register in the printout report. So we have this, then we can go to special objects and we want to use surface contacts. And for boreholes, we also should open this point. We want to have the boreholes in our printout report and the layers, and the layers are described there too. We want to have information regarding our soil massif, and we take the surface supports, the load cases, and the graphics. That's enough for me. We can save and show. Then our printout report is prepared, and it opens up and we can have a short look on it. Okay, we can see it here already. It should open up also. Yeah, it will come. There it is. That's how the first draft of your report, or our report, looks like. We have here a graphic, and with right-click on it, you can easily edit it. If you want to see it in a different way, I would, for example, use the solid display and maybe remove the nodes and so on. And then we can see that it was print what I wish to print. I have the boreholes, the layers, the materials are also there. Here we can see our specific values for each material, and we have massive information and so on. So that's for the input. I now could also, just as information, and as I said, we can print a borehole there. I do go here and say print graphics to printout report, and when I get a draft and this format is fine for me, I say okay, and then it comes to our report directly. And if I don't like the position, I can also move it per drag and drop, and I move it to my boreholes chapter. Then I have my graphic there as an information. Okay, so that's for me now enough for our printout report for the input so far. Now we really could start the analysis, and I prepared this. We have a model that is calculated already so that we have enough time to look at all the results. Okay, so this is the analyzed model. You can just go on calculate or to calculate, and then it's calculated. And here we have the results. Before we look at the results, I want to go with you into our load cases dialog, and I want to show you something. In this model, I also added another self-weight for soil load case just for information. Here I use the classic static analysis setting, and we can compare the stresses and deformations for these different settings. And what I want to show you as well is these load cases. I did uncheck all these other load cases to solve, because as we remember, we have in soil the stress dependency of the stiffness. So in these load cases, we only have the assigned loads. We don't have soil self-weight wear there. And this doesn't make sense. If we remember, we need the stress state, the correct stress state to use the correct stiffness for the analysis. So it doesn't make sense if we take live load as an example. It doesn't make sense to only solve this live load case. There it would be use the stiffness from 0 because we don't have other stress there, and this doesn't make sense. Before the live load is assigned and causes deformations, we already have self-weight of soil there, we have self-weight of structure there, and eventually dead load, and they all cause stress. From that the correct stiffness comes, and with this stiffness the live load should be calculated. So it doesn't make sense to calculate it alone, and it doesn't make sense, and it also can cause problems in the analysis, as it doesn't make sense to use this model and only calculate a live load on there. So you can uncheck them. These loads are used in the load combination, and within the combination they will be analyzed in the right range. Okay, that's that as an information. Now we can go to our results. I at first will go with you to load case 6, to the self-weight of soil load case with the classic static analysis setting. I will bring it to center. We have here the navigator for results, and it is separated into 2 parts. In the upper part you can select which result shall be displayed, and in the lower part you can select how it shall be displayed. And I want to remove the separation lines. Yeah, I prefer this view. Okay, so what we now see is the solids stresses. It's the stresses in Z direction from self-weight of soil. We have here on the right side also the panel for it, and we can see the values for the colors. What I want to show you now too is that our load case 5, that has the other static analysis settings for reset of displacements. If I open this load case, we see that the stresses don't differ. Now it's load case 5, and we see that nothing changed. So the stresses were calculated absolutely in the same way. I go back to load case 6, and now we can have a look at the deformations. And we see the deformations that are caused by soil self-weight. It's around 120 millimeter in this example. And we can understand that we don't need these deformations in our final results. It makes it more difficult to see the results of the building, and we are not interested in them. And that's why we can reset them. And this is what we have done in load case 5 with the specific static analysis setting, and we see now it worked. In our load case 5, the global deformations are 0. So this can be assigned as initial state, and then every further load causes deformation, but this self-weight load didn't cause any deformation anymore here. Okay, so then let's have a look at the stresses again. We now stay in that load case 5. We look at sigma Z. And we have a look at the bottom surface. We see the stress there. We have here around about 280 kilonewton per meter square compression. And if we now go to our maximum combination, where we have assigned all the other load cases, we can check the stress at the bottom surface too. And then we will see how it changed by our building. So with the building here, we have a change of around about 3.7% at the bottom surface, and this is fine. This is it's a good result, so that it shows that our bottom surface is far enough from our building, so it doesn't have a negative influence on the behavior here. And this check you could do with the other surfaces as well. You could check how the stresses at the boundary surfaces are changing, and then you could decide whether you need to have a bigger soil massif or whether you could maybe reduce dimensions and so on. Okay, but we now see that in that direction our soil massif is fine. Then I would like to show you another thing. We can have a look at the principal stresses. We will look at sigma 3, and I want to change the way of display. I want to use the isobands for solids. I select it here and it will come. And now I want to show you a useful setting that you can use when you have initial states. We now do see the final results. We see the results from the geostatic stress state. We see it's now stresses. Yeah, we see in sigma 3 the stresses from soil self-weight, from dead load from the building, from self-weight from the building, and everything. But it is also possible to display the differences to initial state. We remember initial state is the self-weight of soil, so I can check the difference between my final state and the self-weight of soil stresses. And then I see the delta stresses, the stresses that are caused by my building. And I can see how they behave in the depth. This is a quite nice feature. It's, yeah, you can switch between final results and differences. Okay, for these differences, for this situation that we have the results of the building load, I want to have a look with you at the sigma z stresses, at the pressure below the building. We can find here again, and we use the original, the isobands display way of display. Yeah, now we can have a look at it from top, and we can see the pressure below the buildings, and we can use the separation lines if we want to have these values more clear shown. Yeah, that's it for the stresses. Now I would like to go to the deformations. We activate the deformations and we go in this distance and we see the deformation of the whole solid. We can also activate here that we have results on surfaces. It's in our control panel. You can select this, and results on all members. As we can see here, we have now the type of results differences to initial state, but our deformations from initial state are in any way 0, so we can also go to final results and it looks the same in this case. Okay, here we can see how our building settled and how the settlements in the soil look like, and we have a nice feature for having a better look in the inside. We have here at the bottom, you have the menu where you can select the clipping planes, and if you just click it, you get a clipping plane provided, and you can here pick one of these 4 balls and you can move it through your 3D body and have a look inside. And if we go here to the column footings, I would like to stop there. Yeah, and if you want to edit this clipping plane, you also can do a double click here. Then you can enter a value. If you have a specific position where you want to have a look at, you can also do it like this. Okay, so what we can see here now is yeah, an advantage of the finite element analysis of the whole system, the superstructure and the soil together. We can see now that we easily have in our results the effects of influence or the interaction between parts of the structure and the soil. We can see that this slab causes here some settlements around it, and these settlements, they influence also the settlements in these footings of the columns. And these effects you in this quality, you only can reach with 3D finite element analysis. And if we think about that we would have a neighboring building, we would have this influence easily and directly. And if you think about that you would change your building here, you would directly have the change in the settlements. And on the other side, if you would change the solid, you would have the change of stresses in the building through to settlements, caused by settlements. So this is an advantage of the 3D analysis. Now I don't need my clipping plane anymore. I just can click on here and it is gone. Now let's have a look at the soil only. Therefore, I don't want to see results on members and don't want to see results on surfaces. Yeah, and now we can have a look here. Yeah, we see the sediments in the soil like this, and we can also check the deformations of the slab. Therefore, now I can uncheck the solid and I can activate my surfaces, and I did prepare an object selection. Object selections, you can just select, do a right click and create them, and you find them in object selection and guide objects. So I did assign an object selection that contains all surfaces that are placed at the bottom of the building or on the top of the solid. So we can have a look at its deformations and we can see what's happening in the surfaces, in the foundation elements. And if you want to have a look, a more detailed look in it, we provide here our result sections, and I want to create with you one. You can select a point from where the section shall start and where it shall end. I would like to check all the settlements in the footings row. I don't need to cut solids, and I want only results for the surfaces placed on top of the solid, and therefore I can use my object selection. I just click on here and it writes all the surfaces that are contained in that dialog. I say OK, and I have my first result section. Here in this panel you can set the display factors, and I want to bring it upwards so we can see our results section more clear. In the navigator for results, I can also modify the way of display, and I would like to see more values. So I can see what's happening in these footings of the columns more in detail. And I would like to do another result section. This one I would like to do from this end of this wall up to the, let's say, the footing with the most settlements. And again, I want to select in which objects I see results. And again, I use my object selection. I have the surfaces there, and we can see in this direction too. And now I can see quite clear the values for this line in my slab. And if you want to see further or more details, you also can select this section, this result section, and go to result diagrams. And there you can see it. You can get more information, and I only want to see the deformations now. Here we have surface 1, and here we have surface 24, which is our footing. And yeah, I can also print this to printout report. Here I can say print graphics to printout report, and it prints it to our prepared report. It looks fine to me. I say OK, and I can also select my first result section and directly print it to the report. It gets the same settings as the one before, and it also looks fine. And maybe as an additional information, I could also give an overview, and yeah, here we can see both. We can also print this Here you can go on File, Print Graphics to print out report, and you also can use this key combination. Here you get a preview also. Yeah, it looks good to me. It's good as an overview. I say save and show. And then our printout report for the solved model opens up. This was my aim. This was the aim of this webinar. I wanted to show you geotechnical analysis, and we wanted to see the results for settlements and the pressure below the building. Now I would like to show this in the report. I did prepare some graphics for all the steps we looked at. They are contained in that report, and we can just summarize this. It opens up, unfortunately, a bit slow because of GoToWebinar presentation. But here we go. Yeah, this graphic I changed the settings and it looks much better, as you saw before. Here we have our profile added, and I also did add the loads to this, the load cases to this report. And here we can see our results, what we looked at. We checked the sigma Z for load case soil self-weight for the load combination with the building. We saw the principal stresses sigma 3 and the sigma Z below the building. And we also looked at the deformations. And the surface deformations we checked. And this is what we printed. And I can also remove this overview before this, then it makes more sense. And as you see, I did prepare it in German. You can switch the language in our report quite easy. You can work in your language and change it for your customer. And yeah, by one click. Okay, this is what I wanted to show in the end for the report as an overview. Now, before I give my word back to Andreas, I would like to come back to the presentation. I have some 2 last slides. Cannot switch it right now. Then let's go to here. And so we learned the topic. Yeah, now it works again. This is what we learned. We can go to the next page of the slide. This slide we will also provide to you with the webinar files. And here I have a slide that summarizes some further links that are connected with the topics we spoke about today. Here you can find some links to web service, some introduction, this is the online manual and a webinar that is quite good. I also put some further geotechnical analysis webinars we have, and also the link to a webinar regarding construction stage analysis. As for the higher soil material models, it's quite common to use the construction stage analysis, because you can then more in detail consider the stages of the construction and the loading, and therefore the correct stiffnesses, as we remember the correct stress states and the correct stiffnesses in the soil. So it's connected to our topic. That's enough for this one. Now we come to the final slide. I would like to summarize that in Rfem 6 we provide to you an analysis for the superstructure and the substructure in one model. So we have soil structure interaction fully integrated, and you can quite comfortable consider the influences between different parts of the building or different buildings as well. And the finite element analysis, the 3D finite element analysis for soil provides a displacement calculation to you with superior quality, of course. And another hint is that the geotechnical analysis combined with construction stages, it is an ideal tool, or can be an ideal tool for comparing your expected behavior with measurements at the site. If you have a project that is sensitive according settlements, it can be quite useful to compare it with the calculation and check whether the settlements are as expected or not, and you should have a look at it more in detail. This just as a short summary. Then as prospect, as I said, we have 3 further material models in work. The first one that will come is the Hook-Brown model. This one we will release quite soon, in the next days, let's say. And we have the hardening soil model. It is already actually implemented. We are just testing it quite intensively, and it shall be provided in the second quarter of this year. And the Chem Clay model, we started. The development has started for it. We also have the pile foundations in progress. This will come, and we have the geotechnical stability analysis planned. Yeah, that's it as prospect from what's going on in our team for you. Yeah, now I finished the aim of the webinar for today. I would like to thank you for your participation, and yeah, I would like to give my work back now to Andreas, to you. Then, bye-bye.
Thank you, Juliana, for this nice presentation. Before I show you the website where you can find the recording and the models and the slides and so on, I would like to, sorry, one moment, please. I would like to invite you to the digital Bau in Cologne. You can secure your free ticket. Yeah, just book a live demo with that link here, or you can scan that QR code and you get or you can choose an appointment, and yeah, then we will send you the free online ticket. If you can't come to the digital Bau in Cologne, you can book your free online appointment every time. Just contact our sales team, also with that link, or you can scan that QR code. You can get a free product demonstration, or if you want to get a non-binding offer for any of our products, just contact our sales team. So then I switch to our website, dlubal.com. Under News and Events, you can find the webinars. Those are the webinars of the next weeks. Our wind, then timber floor calculations, the FAQ webinar that we present regularly, then calculation of reinforced concrete slabs, connection with circular hollow sections, optimization, and that's today's webinar. It's also already a previous webinar. I click on it. In the next days, you will get an email with your certificate and with a link directly to that page. Then you will find the recording in the middle here. You can already download the presentation slides and the webinar files. And there's also the model that you can download. Okay, that should be also all from my side. Thank you for your attention. I hope we meet each other in another webinar. Thanks to Juliane for the presentation. Thanks to Alexander for the support by answering the questions. I wish all a nice rest of the day, and bye-bye.
Bye.